So in the previous video, I have already shown you the direction of current from higher potential to lower potential and the utilization of Ohm's law, that is V equals to IR. So I am writing the concept again. So higher potential to lower potential. This is the direction of current. And number 2, Ohm's law, V equals to IR, right? Where V is the potential difference between two terminals, I is the current through them, current through the conductor, and R is resistance. Units are important. The units are potential difference, that is V, this unit is volt, the unit of current is ampere, and the unit of resistance is ohm. You can also write like OHM, ohm. Okay, so today's video is dependent on the circuit analysis. Write down circuit analysis. What do you mean by circuit? Circuit means is the combination of some electrical elements, okay, like resistor, battery. So now how to analyze a circuit? What is the meaning of analysis? You have to calculate the voltage, the potential differences, the potential of any point, the current through any path. You can calculate by using this Kirchhoff law. Okay. Some people pronounce like Kirchhoff's law, but it is actually Kirchhoff. Okay, its name is Kirchhoff. So Kirchhoff's law, there are two Kirchhoff's law. Okay, number 1 is KVL, and number 2 is KCL. KVL means Kirchhoff's voltage law, and KCL means Kirchhoff's current law. Don't pronounce it as Kirchhoff's, it is always Kirchhoff's current law. Okay, so by the help of these two laws we can analyze any circuit in this earth, any circuit. First I will explain KCL, that is Kirchhoff's current law, and then I will move into Kirchhoff's voltage law. Both the laws are very easy, okay, and there is no basic difference actually. You will understand very well. So now write down KCL, Kirchhoff's current law, and now forget about KCL and think about one practical example. Okay, you may ask, what is this? This is a very weird thing I have drawn here. These are some pipes, okay, water pipes. Suppose waters are falling from these three terminals, okay, from these three terminals, 1, 2 and 3, and the water will flow into these pipes from here, here and here. Okay, so the total amount of water will be here, incoming water, and due to gravity the whole water will fall from this and this pipe. Okay, now it depends on the width of the pipe, but somehow the whole water will fall from it, right? Now you tell me, will any water stuck here? No, the whole water will be fallen out. So what does it mean? No water will be conserved by this system or this pipe. So can I write like total incoming current, this from here, here and here, is equal to total outgoing current from this and this terminal, because no water is being stored here in this system, which means the net amount of flow of water will be zero. The net amount of water will be zero because the incoming current will be equal to outgoing current. So the whole amount of water will be removed out. So there will be no water storage. One more practical example, maybe is a four-way crossing, maybe it is Shambazar crossing. Okay, Shambazar, the statue of our greatest hero. So maybe this is BT road. Okay, say two cars are coming from this path, three cars are coming from this path. So here 2 and here 3. How many cars are there? 5. Now just imagine, no car will stand here, right? each and every car have some certain destination, so they will move towards their destination. Maybe they will go from here 1 2 3 4 5. So just see here, 3 plus 2, 5 cars were coming from these two paths, and these 5 cars are going out from these two ways, which means there will be no storage of car. No car will stand in this middle. Same here, no water was stored here. Here we can also write that number of incoming cars is equal to number of outgoing cars. Clear? Now write down the statement of KCL. The algebraic sum of current in a particular node, underline this term, node of a circuit, is equal to 0. So the algebraic sum of current in a particular node of a circuit is equal to 0. What do you mean by node? Okay, node is the interconnection of more than one branches. Suppose this is one electrical branch where a resistor is connected R1. Okay, and from this point another path is there, which may be R2. Another point is there, which is R3. Now see, in all these three paths, R1, R2 and R3, this point is common, so it will be considered as a node. Clear? Suppose there are 6 paths, 1 2 3 4 5 6, and see, this is the common point, so it will be considered as a node. Okay, now maybe a current I1 is coming from this path toward the point. A current I2 is coming towards this point. Maybe the direction of current I3 is outward. It can be any direction. Okay, maybe I4 is again inward. Maybe I5 is outward, and I6 may be also outward. So it's not necessary. Now just imagine, compare with this case. Okay, here the incoming current is equal to incoming water is equals to outgoing water. Here the incoming cars is equals to number of outgoing cars. So similarly, this is also like of one kind of pipe system where I1, I2 and I4 currents are incoming, and I3, I5 and I6 currents are outgoing. So incoming current equals to I1 plus I2 plus I4, and outgoing current equals to I3 plus I5 plus I6. So from the pipe convention, we can consider that here also the net incoming current is equal to net outgoing current, like this. So incoming current is equal to, and outgoing current equals to, like this. So now if I solve this equation, it will be like this. So I3 is minus I3 here, I5 is minus I5 here, and I6 is minus no, I6 is plus I6, no problem, is equal to 0, because no terms is left on the right hand side, so it will be 0. Now see, what do you mean by algebraic summation? Algebraic summation means we consider the direction of flow. Okay, so here we have considered the incoming currents to be positive and the outgoing currents to be negative. I6 should be negative. Okay, so I3, I5 and I6, these are outgoing currents, so this we have considered minus. Okay, from the equation only we can solve it. So we can write sign convention to be incoming current equals to positive and outgoing current to be negative. But let me tell you one thing, this is not universal truth. Okay, incoming current must not be positive. See, in this equation, if you multiply the whole left hand side and right hand side by -1, the equation becomes minus I1 minus I2 plus I3 minus I4 plus I5 plus I6. Now see, in this case the incoming currents are negative, minus minus minus, right, and the outgoing currents are positive, positive positive. So the sign convention may also be, or incoming current to be negative and outgoing current to be positive. So it depends up to you. Okay, depends on you. that which convention you will consider, but in my case I prefer this. Okay, I don't know why, but I think it's easy to understand why, because incoming current means currents are increasing, so it is positive, and outgoing currents means the currents are decreasing, that is why it is negative. I have considered this one, but again I am saying this is not universal truth. You can consider this also. Okay, so it is up to you, so don't be tensed. Now see, the statement of KCL is the algebraic sum of current. Now what do you mean by algebraic sum of current? It means we are considering the direction also. If you are considering the incoming current to be positive, then you have to consider the outgoing current to be negative. Or if you are considering the incoming current to be negative, then you have to consider the outgoing current to be positive. The sign should be opposite to each other. Nothing more than that. So according to KCL, just look into this small example where I1, I2 and I3 currents are incoming or coming towards the point or node, and the I4 coming is going out. So by using this kind convention, I am considering the incoming current to be positive. So plus I1 plus I2 plus I3, and the I4 current is going out. So I am considering this to be negative. I minus I4 equal to what? See, I have considered the algebraic summation. Okay, that is why incoming currents are positive and the outgoing current is negative. It should be equal to 0. So this will be 0. Clear? Now see, you can send this minus I4 into RHS. So this will be I1 plus I2 plus I3 equals to I4, which means sum of incoming currents equals to sum of outgoing current. Now see, what is the definition of electric current? Electric current is denoted by I, okay, that is flow of charge per unit time through a conductor. Charge is denoted by Q. Now see, let dq, very small amount of charge, is passed through a conductor in dt time. Okay, so if in dt time the amount of flow of charge is dq, then what will be the amount of flow of charge per unit time? That will be equals to dq by dt. Why? Because dq amount of charge is passed through a conductor in dt time, therefore charge per unit time is dq by dt. That is equal to electric current. So electric current I is equals to dq by dt. Remember this one. Now see, here I have taken another example. I1, I2 and I3 currents are incoming, and I4, I5 and I6 currents are outgoing. So from the concept of net incoming current equals to outgoing current, we can write I1 plus I2 plus I3 is equal to I4 plus I5 plus I6, because we have learned that incoming current is equals to outgoing current. So here the incoming currents are I1, I2 and I3. Therefore incoming current equals to I1 plus I2 plus I3 is equal to I4 plus I5 plus I6. These are the outgoing currents. Now see, we know the relation between current and electric charge, that is I equals to dq by dt. Okay, so in place of I1, can I write dq1 by dt? Say dq1 amount of charge is passed through a conductor in dt times, so amount of charge passed through the conductor per unit time will be dq1 by dt. Similarly, this will be dq2 by dt, this will be dq3 by dt, and all these are can be written like this. So dq4 by dt plus dq5 by dt plus dq6 by dt. Okay, so see here one thing is common, that the amount of time dt 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 dt. So this can be cancelled out, dt can be cancelled out. So the equation is like this: dq1 plus dq2 plus dq3 is equals to dq4 plus dq5 plus dq6. So now see, these are the differentiated values of charges, very small values. Okay, now if you want to get the main values, you have to integrate this equation in LHS and RHS. So integrate all these terms, integrating both sides. So dq1, if you integrate dq1, it will be okay. Now see, if you integrate dx, becomes x. Okay, x plus c maybe, but we are neglecting the error here. Okay, we are neglecting the plus c here. So integration of dx means x. So integration of dq1 means q1. dq2 will be q2. It's like q1 q2 q3 equals to q4 plus q5 plus q6. Do you know what does it mean? It means total incoming charges q1 q2 and q3 is equal to total outgoing charges, that is q4 q5 q6, which means just like exactly similar to this example where no water was being stored. Similarly here no incoming charge is being stored here. Okay, the whole amount of charge will be removed or go out. So total incoming charge is equal to total outgoing charge, and it is the conservation law of charge. So this is conservation law of charge, which means KCL, Kirchhoff's current law. KCL supports conservation law of charge or conservation of charge. So this is the concept of KCL. Okay, so now we have to learn the application of KCL. Okay, and we'll learn it in the next lecture. Before going to the next lecture, you have to understand that total amount of current incoming, total incoming current is equal to total outgoing current, and similarly total incoming charge is equal to total outgoing charge, and this means the conservation law of charge. So KCL supports conservation of charge. And also one thing, decide today that which sign convention will you choose, this one or this one. Okay, again I am saying I will prefer this one because it is easy to understand. Okay, consider any one, don't be confused about this. So the application of KCL will be cleared in the next lecture. Okay, goodbye.